Okay. The most important application. The most important application. The most important application. The most important application of acid base solutions containing a common ion is for buffering. Okay. So a buffered solution is one that resists a change in its pH, when hydroxide ions or protons are added. Okay, so that is how we can define a buffer. A buffered solution is one that resists a change in its pH when hydroxide ions or protons are added. Okay, so the most practical example of a buffer is our blood. It's our blood. Okay, so we know that a constant pH for blood is vital because cells can survive only in a very narrow pH range. Okay. A buffered solution may contain may contain a weak acid and its salt. So number one, a weak acid and its salt. A weak acid and its salt. For example, like the one that we have looked at, hydrofluoric acid and sodium fluoride. This forms a buffer. Okay, and here there's a common ion. That is the fluoride ion. Okay, and also we can have a buffering system with a weak base and its salt. A weak base and its salt. A weak base and its salt. So we know that ammonia is a weak base, so we can have an example of ammonia and ammonium chloride. Okay, that forms a buffer. All right, so straight away we shall now look at ways in which we can now calculate the pH of a buffered solution. Okay, so the pH, we know that pH is equal to negative log hydrogen concentration. So that one, normally we use it for strong electrolytes, but here we are dealing with weak acids and weak bases, so we cannot straight away use that formula direct. Okay, so let's have an example. Let's see how we can determine the pH of a buffered solution. Okay, so the pH of a buffered solution. the pH of a buffered solution. A buffered solution contains a buffered solution. A buffered solution. A buffered solution contains a buffered solution contains 0.5 molar acetic acid. 0.5 molar acetic acid, HC2, H3O, O2. So that is the formula for acetic acid. Acetic acid. Then the Ka for acetic acid, Ka is equal to 1.8 times 10 to the power negative 5 times 10 to the power negative 5 and 0.05 molar sodium acetate. Sodium acetate, that is the salt. Okay, sodium acetate. Okay, sodium acetate. Calculate the pH. Calculating the pH of this solution. Calculating the pH of this solution. So this is the question. Okay, so now we calculate the pH. We calculate the pH solution. Okay, so here we have the weak acid, that is acetic acid, and its salt, sodium acetate. Okay, so we can straight away write the dissociation equation. So acetic acid aqueous would dissociate to form, so it will lose that hydrogen ion. Okay, plus we now have the conjugate base C2H3O2. Okay, so this is the dissociation equation. So we can use the ICE table. ICE. Okay, so the initial concentration of the acid is given 0.5, hydrogen 0. For the conjugate base is also 0.50. Okay, so change minus x plus x plus x. Equilibrium 0.50 minus x 0.50 plus x. Okay, so this is the ICE table. Okay, so now we know that Ka is equal to concentration of hydrogen ion times the concentration of the conjugate base over concentration of the acid, HC2H3O2, which is equal to Ka is given, that is 1.8 times 10 to the power negative 5. Okay, then now we substitute equilibrium concentrations. Ka is 1.8 times 10 to the power negative 5. 1.8 times 10 to the power negative 5, which is equal to concentration of hydrogen is what? X. Okay, Then concentration of this, the base, 0.50 plus x, over concentration of the acid, 0.50 minus x. Okay, so to solve for x, we apply the 5% rule. Okay, so x is very small, so we neglect x, so it will be x over 0.50 over 0.50. Okay, you can see that this will go, which is equal to x. Okay, so in this case now, x is equal to 1.8 times 10 to the power negative 5, which is now equal to, which is the concentration of hydrogen ion. Okay, so now we are going to so from the table, concentration of hydrogen ion is equal to x, which is equal to 1.8 times 10 to the power negative 5 molar. Okay, so now from there we can calculate pH. pH is equal to negative log hydrogen ion concentration, which is equal to negative log 1.8 times 10 to the power negative 5. So which will give us so we do the computation. So when you punch negative log 1.8 exponent negative 5 on your calculator, you are going to find 4.74. Okay, so this is the pH of this solution. Okay, so now we have found that the pH of this solution is equal to 4.74. So now we want to see the pH changes that can occur if we add, suppose we add 0.01 more sodium hydroxide to 1 liter, to 1.0 liter of the buffered solution. We add this. Suppose we add 0.01 more of sodium hydroxide to 1.0 liter of the buffered solution. Okay, of the buffered solution. Okay, so what will be the changes in the pH? Are there going to be any changes in the pH of this buffer after adding that base? Okay, so now let's see what will happen if we add 0.01 more of sodium hydroxide to 1 liter. Okay, so you can see that the volume here is 1 liter, so which is just the same as 0.01 molar. Okay, since moles is equal to molarity times volume. Okay, so now let's see what will happen. Upon adding that to this buffered solution. So we take note of the pH that we have found. Okay, so now we are adding 0.010 more sodium hydroxide to 1 liter of the buffered solution. Okay, so now if we introduce sodium hydroxide, sodium hydroxide is a strong electrolyte. It's a strong electrolyte which completely ionizes in solution. So this sodium hydroxide will give us, it means now we are adding hydroxide ions. We are adding the hydroxide ions that have a high affinity for protons. Okay, so these hydroxide ions now will react with the acid, with a weak acid, acetic acid. So acid, which is HC2, H3, then plus OH, okay, it will react with the acid plus OH, okay, then this now will give us what? It will be neutralization in reaction. Okay, so we are going to have the conjugate base, which is C2H3 or 2 aqueous, then OH plus that hydrogen, it will now form water. Okay, so that is the equation. That is the equation that will result when OH is added to this buffered solution. Then now we need to determine the concentrations before and after. Okay, so before reaction, then here we'll say after. So the before reaction and after reaction, before reaction and after reaction. So before reaction, we know that the concentration, so we can either work with moles or concentration. Okay, so let's work with moles. Since it is in 1 liter, so 1 times the same, it will be, we know that moles is equal to MV, molarity times volume. So volume is 1 liter, so the number of moles is equal to the concentration in this case. Okay, so for acetic acid, the concentration of acetic acid is what? 0.50 molar, so which is 0.50 moles. Okay, we have multiplied using MV. Okay, 1 times that, which is that. Then the concentration of hydroxide ion, 0.010 mole. Okay, then the concentration of the conjugate base, which is 0. Initial, that is before 0.500 mole. Okay, so water is neutral there. Okay, then now after reaction, so we expect this to happen, so it will be now 0.50 minus 0.010 moles. Okay, so which will give us now, so you 0. Since the OH will be consumed by the acid. Okay, so 0.50 minus that, it will give us 0.49. So we have 0.49 moles. Then here it will now give us 0, since 0.01 minus that. Okay, so here we are going to have 0. Okay, so it's like after reaction now, it will be 0.01 minus 0.01. Okay, which is 0. Then here now it will be 0.01 plus 0.010. Okay, that's a conjugate base, so meaning that it will increase in concentration, so it will now go to 0.50 moles. Okay, so these are the new concentrations that we have. Okay, so for the acid we have 0.49 OH0, then the conjugate base, that is 0.51. Okay, so now we are now going to write the ICE table. We are now going to write the ICE table. So we write now the dissociation equation for the acid. The dissociation equation now for the acid. So we know that acetic acid will dissociate to form hydrogen ion plus C2H3O2 aqueous. Okay, so that is the dissociation equation. Then ICE. Okay, so now the initial concentration of acetic acid in this case is 0.49, the one that we have found after addition of the solid sodium hydroxide, hydrogen 0, then this one 0.51. So here it will be minus x plus x plus x plus x. Okay, then equilibrium 0.49 minus x 0.51 plus x. So these are our equilibrium concentrations. So we do the same. Ka is equal to hydrogen ion concentration times C2H3O2 negative, then over HC2H3O2, which is equal to 1.8 times 10 to the power negative 5. Then now we substitute initial equilibrium concentrations. So we have 1.8 times 10 to the power negative 5, which is concentration, which is equal to concentration of hydrogen, which is x, concentration of this, it's there, 0.51 plus x, over concentration of the acid, which is 0.49 minus x. Okay, all right, so x is so small. In this case it will be x over 0.51 over 0.449. okay, so you can divide that number and divide it into that to get x. Okay, so x in this case, when we do our arithmetic, we are going to find x is equal to 1.7 times 10 to the power negative 5. Okay, which is now equal to the concentration of hydrogen. So hydrogen ion is equal to x, which is equal to 1.7 times 10 to the power negative 5 molar. Then now pH in this case is equal to negative log that 1.7 times 10 to the power negative 5 molar, which will give us 4.76. Okay, so you have seen after adding sodium hydroxide, the pH now, this is a new pH. pH. Okay, it has increased slightly from 4.74 to 4.76. Okay, so now let's determine the increase, the change. Let's determine the change in pH. Let's determine the change in pH. Okay, so the pH has increased. The new pH is 4.76, then minus 4.74, which is giving us 0.002. Okay, so this is the new pH. Then this one is the original. This is the original pH. Okay, so the pH has increased by, we have seen here the pH. So pH has increased by 0.02 pH units. 0.02 pH units. Okay, which is minimal. It's not very much. Okay, so you have seen the buffer here has resisted, though a change is there, but it's very minimal, has resisted the change in pH. Okay, so now let's compare this with pure water. Okay, we know that the pH of pure water, is around 7. Okay, that is 7.00. Okay, so now what happens if we add? So if we add 0.01 molar of sodium hydroxide, we add the same to pure water. Okay, so if we add 0.010 molar of sodium hydroxide to 1 liter of water, to give a concentration of 0.01 molar sodium hydroxide, what will be the change in pH? Okay, so since sodium hydroxide is a strong electrolyte, in this case we know that the concentration of the concentration of hydroxide ion is 0.01 molar, strong electrolyte. Okay, so now we can determine if we know the concentration of OH, then we can find the concentration of hydrogen ion using the equation. Hydrogen ion is equal to Kw over hydroxide ion. Kw, that is water dissociation constant, so which has a value of 1.0 times 10 to the power negative 14. It's a constant. Then over concentration of hydroxide ion 0.01. So if you divide that, you are going to get 1.0 times 10 to the power negative 12. Okay, then now we find the pH. pH is equal to now negative log hydrogen concentration, which is here. So negative log 1.0 times 10 to the power negative 12, which is giving us 12. Okay, so the pH is the pH now will go to 12. Okay, so now let's calculate the change in pH. So the change in pH now, it will be 12.00 minus the pH of pure water, which is 7, which will give us 5, positive 5 pH units. Okay, so now you can compare. When the same concentration was added to a buffer, the change was only positive 0.02 pH units. But when added to pure water, you can see. So you have seen that a buffer greatly resists the change in pH. Okay. So now we can now look at other ways of calculating pH. Okay, we can now look at other ways of calculating pH. Buffering, how does it work? Okay, so there are so many steps that we want to derive a certain equation. Now there are so many steps involved. We are not going to show all of them. We'll just give them the actual equation. Okay, so pH can also be calculated by this log equation. pH is equal to pKa plus log A minus over HA. Okay, so that is the conjugate base over the concentration of the conjugate base over concentration of the conjugate acid, which can also be written as pKa plus log base concentration over acid concentration. Okay, so pH is equal to pKa plus log base concentration over acid concentration. Okay, this equation is called the Henderson-Hasselbalch. It is called the Henderson-Hasselbalch. The Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation. So we can use this equation to calculate the pH of a buffered solution. Okay, so if we have two buffers with the same ratio, if the two buffers involved, if you have two buffers involved which has the same ratio of the conjugate acid, conjugate base, conjugate acid ratio is the same, it means the two buffers will have the same pH. If this ratio is the same ratio, then it will give the same pH. Suppose example, suppose we have a buffered solution with 5.0 molar acetic acid, 5.0 molar acetic acid, 5.0 molar acetic acid, and 3.0 molar sodium acetate. 3.0 molar sodium acetate. Then another buffer B contains 0.050 molar acetic acid. Then another buffer, then the salt is 0.030 molar sodium acetate. Okay, so buffers A and B, buffers A and B who have the same pH will have the same pH. How? will have the same pH. Okay, so we are now looking at the ratio of the base over acid. So for A, the ratio is 3.0 over 5.0, which is giving us 0.60. Then for B, the ratio is 0.030 over 0.050, which is also giving us 0.60. So you can see the ratio is the same. So when you divide there, since they have the same ratio, meaning that it will be log that, it will be the same. Okay, since they share the same Ka. So the pH of these two solutions will be the same. Okay, so now let's see how we can use Henderson-Hasselbalch to calculate the pH of a solution. The pH of a solution. Okay. So we can have an example. They calculate the pH. Calculate the pH of a solution. Calculate the pH of a solution containing 0.75 molar lactic acid, which has a formula HC3H5O3. So Ka for lactic acid is 1.4 times 10 to the power -4, and 0.25 molar sodium lactate. Okay, so we know this sodium, for example, lactic acid is a common constituent of biological systems. It is found in milk, and also it is present in human muscle tissue during exertion. Okay, then we can now calculate solution. pH is equal to pKa plus log base over acid. Okay, so straight away we use this. So we have two options. We can either use an IC table or Henderson-Hasselbalch. Okay, so pKa, Ka is given. So pKa means negative log Ka. Okay, so now we do negative log 1.4 times 10 to the power -4. So negative log that will give us negative log Ka, that is 3.85. That is the pKa. So you bring it in 3.85 plus log base. Okay, concentration of the base 0.25 over, you know that the units will cancel, so over 0.75. So you divide that So 3.85, then plus, so in this case it will be minus, then minus 0. 0. So when you divide that number, then you find the log. So the log of that, the result of this division, that is 4.7. So which is, when you subtract, you are now going to get 3.38. Okay, 3.38. Okay, so that is the pH of this solution. Then now suppose we use the ICE table. So let's do it. Let's use the ICE table. We see if we are going to find the same. Okay, so that is by using HH equation. So by using the ICE, let's dissociate the acid. Okay, so lactic acid will form hydrogen ion plus the conjugate C3H5O3. Okay, then ICE. Okay, so the initial concentration of the acid 0.75, 0 there, 0.25. So minus X plus X plus X. So it will give us 0.75 minus X, 0.25 plus X. Okay, so that is the ICE table. Then now we write Ka expression. So Ka will equal to concentration of hydrogen ion, then C3H5O3 minus over acid HC3H5O3, which is equal to, K is given 1.4 times 10 to the power negative 4. Okay, K is given. Then now we substitute the equilibrium concentrations. Ka 1.4 times 10 to the power negative 4. Hydrogen X over conjugate 0.25 plus X over acid 0.75 minus X. X is so small, neglect X by 5% rule. So X, it will be X 0.25 over 0.75. Okay, so now you divide there and multiply. So we are going to find our X. So let's now calculate X. So when we calculate X, we shall find that our X is equal to, okay, so we divide this number and that. Okay, so now X value, so now we calculate the X value. Okay, all right, so in this case now you know what to do. You can simply, since this one is now straightforward, I don't have the calculator to calculate, so it will be 1.4 times 10 to the power negative 4. So this is the equation. Okay, so to find the X now, it will be X is equal to 1.4 times 10 to the power negative 4 times 0.75, which is equal to 0.075, then over 0.25. Okay, so the value you are going to find here will be equal to the concentration of hydrogen. Okay, to be equal to the concentration of hydrogen. So hydrogen concentration, so you can do it alone. So hydrogen concentration is equal to X. That will be the value that you are going to get here. Okay, then after getting hydrogen concentration, now apply the equation. pH is equal to negative log hydrogen concentration. Then I'll compare the pF we are going to find and the one that we found at first. Okay, so the one we found at first is pH is equal to 3.38. Then compare now using the value of x, the one that you are going to find here. Okay, so we can end here. We can end here. Then the next lecture we shall look at, it will be, we are now going to calculate the pH of a basic buffer. Okay, all right, so we can also have so a buffered solution can also contain, let's say, ammonia and its ammonium, a weak base and its salt. Okay, so the ones that we have looked at is for a weak acid and its salt. So in the next lecture we shall look at weak base and weak acid. Weak base and weak acid. That's the one that we shall look at. Okay, so we can end here. Thank you.